Hello everyone, in this video we're going deep dive into the world of microprocessors. We'll cover how a CPU works, the evolution of CPUs based on 4 key videos, an overview of GPUs, SAP1 operations, and SAP1 programming, and, and how a CPU works. So let's get started. I'll turn off my camera and I'll have you watch a video in the background while I talk.
The CPU, short for Central Processing Unit, is like.
Oops. Okay, for CPU, to understand how a CPU works, we need to break it down into a key component and processes. And at its core, the CPU or central processing unit is the brain of the computer. It executes instructions from programs through a process called the fetch, decode, execute cycle. The three cycle, which how a CPU works. So in fetch, the CPU retrieves an instruction from memory or RAM. The second is decode, which the instruction is interpreted by the control unit, and execute, the arithmetic logic unit or ALU, or other components carry out the instructions. Other critical parts include the registers, which are small storage locations inside the CPU for quick access to data. Cache memory, faster than RAM. It stores frequently used data to improve speed, so it uses it since it's stored always there. Clock speed determines how fast a CPU can process instructions. They are measured in gigahertz. Pipelining allows multiple instructions to be processed simultaneously for efficiency. Control unit directs the flow of data within the CPU. And bus systems, which are the things you can see in the circuit that have those like a raceway lines. So let's take an example. Suppose you are running a simple addition program, just adding. The CPU fetches the instructions to add two numbers, decodes it to determine which operation to perform, and then execute the addition using the ALU. This result, uh, where they are stored in a register or memory, ready for use by another instruction. So now let's move on to evolution of CPU from part 1 to 4 here. So let's start. So first one is the evolution of CPU processing. Part 1, the mechanics of CPU. Try to open my cam. So let's go through the evolution of CPUs. So using insights from the 4 videos provided. So during 1960s and 1970s, multitasking began gaining traction in mainframe computer. Early implementations were crude, relying on multi-programming, where programs were processed in batches. This later evolved into time sharing, allowing multiple programs to run more efficiently. And by the late 1960s, operating systems like DEC's PDP-6, IBM's OS 360 MFT, and Multics introduced true multitasking. Multics heavily influenced Unix, which became a foundation for modern operating system. So the key issue in early CPUs was resource management. Initially, a single program but uh, had full control over the CPU, leading to inefficiency, instability, and security concerns. The solution was multitasking, where CPU focus is shuffled between concurrent processes. So it's one by one instead of handling multiple things at once. So cooperative multitasking, early OSs relied on processes voluntarily returning control to the OS, leading to stability issues. Preemptive multitasking introduced time slices to ensure fair CPU access across processes, improving reliability. Memory management, or MMU, a hardware layer between the CPU and RAM that prevented unauthorized memory access and enabled secure interprocess. Next is virtual memory, which provides an abstraction layer for memory, mapping logical addresses to physical ones, increasing flexibility. So by the 1980s, CPU architecture evolved to support multitasking um, at the hardware level. So here are some uh, examples. So the Motorola 68K, which are from Apple, is Macintosh. It's me. It's an early adoption of 32-bit internal architecture, but operated in a hybrid 32-16-bit mode. The IBM PC-80 or Intel 80-86 introduced protected mode, enabling full multitasking and memory protection. Its segment descriptors and global local descriptor tables, GDT and LDT, ensured secure access to memory. And instruction prefetching, the 80-86 introduced an 8-byte prefetch queue to decode multiple instructions in advance, improving execution speed. So, this innovation laid the groundwork for modern CPUs where multitasking, memory management, and instruction pipelining are now essential, which bring us to the rise of x86. Uh, as in the 1970s, where the the implementation of CPUs progressed, CPU designs became more robust, featuring faster clock speeds, larger address capacities, and more elaborate instruction sets. Intel's next major contribution to this evolution was the 8008. One of the innovations of 8008 was indirect addressing. An instruction fetches data from a specific memory. In an indirect addressing, however, the memory location contains a pointer to another address where the actual data resides. This allowed for more flexible memory management. The 8008 also introduced interrupts, which enable hardware signal and internal CPU events to pause program execution and jump to a high priority code segment. Example include real-time clock signals, internal hardware triggers like keyboard input and internal CPU state. So even software changes could trigger interrupts. After executing the interrupt service routine, the original program would resume, making the CPU more responsive. Intel next major breakthrough was the 8080. It was the first Intel processor to utilize an external bus controller, support chip that managed a communication between the CPU and the system components like RAM and the I/O devices, which are keyboards and mouse. This allowed the CPU to handle memory and input I/O operations effectively and efficiently, even when this operated at lower speed than the CPU itself. Additionally, the 8080 improved electrical noise immunity, making it more reliable. Now, uh, let's move to part three, which is the evolution of multitasking and memory management. So for part three, so during the 1960s into the 1970s, multitasking paradigm was gaining traction in the mainframe world. Initially, the concept was implemented in a cruder form known as a multiprogramming. Multiprogramming was accomplished by processing programs in batches, jumping between them during regions of code that wait for hardware input. This would eventually evolve into time sharing, which is the origin of modern operating systems. So, in the late 1960s, true multitasking started to emerge in operating systems, such as DEC's PDP-6. So, we have already discussed this, Multics, 360 MFT. In a traditional single process environment, the program being executed generally has a full control of the CPU and resources. This creates issues with efficient CPU utilization, stability, and security as software grows more complex. Now, in multitasking, CPU is shuffled between concurrently running processes. Cooperative multitasking was used by many early multitasking like operating systems. Whenever a process is preemptive multitasking, solve the sorry. Whenever a process is given CPU focus by the operating system, it relies on the process itself returning control back. So preemptive multitasking solved the stability problems of cooperative multitasking by reliably granting each process a regular period or time slice of CPU focus. To ensure memory protection and controlled access, uh, a dedicated layer of hardware was introduced between CPU and RAM, known as the Memory Management Unit, MMU. If a process attempts to access memory outside of its permitted range, a hardware fault is triggered. So some MMUs also incorporate memory access privileging, assigning levels of access to memory regions. This prevents lower privileges processed from tampering with critical system code or memory. Virtual memory is another key memory management technique. It provides an abstraction layer between logical memory address and physical storage locations. This enables efficient memory utilization by allowing process to use more memory than physically available. So in January 1983, Apple released the Lisa, which was soon overshadowed by Macintosh in 1984. The Macintosh ran on the Motorola 68K CPU, which, despite being a hybrid of 32 16-bit processor, supported a simple form of multitasking through privilege levels. By late 1984, IBM released the IBM PCIT 80, very uh, which is the most popular one, featuring the Intel 80 to 86 processor, one of Microsoft's major software projects. Windows began development in 1981 and made its first public debut on November 10, 1983. So the 8286 was groundbreaking as the first mass-produced CPU to support multi-user multitasking systems. Uh, so it featured a separate address buses, eliminating multiplexing, a dedicated memory addressing unit for improved access control, an enhanced prefetch unit capable of decoding up to 3 instructions in advance, protected mode, allowing access to 16 MB of RAM, and enabling multitasking. So protected mode, what is it? So it is uh, introduced segment descriptors, allowing read-write protections on memory segments. Violating these rules triggered an exception forcing an OS to interrupt. So the 80 to 86 MMU managed memory via two tables. These are the global descriptor table, GDT, and the local descriptor table, LDT. Together, they could address up to 1 gigabyte of virtual memory. And next is the interrupt descriptor table, or IDT, further refined protected modes interrupt management, distinguishing it from real mode operations. Many consider the 8080 the first truly usable microprocessor. However, Intel faced increasing competition, particularly from the Zilog Z80, which became dominant in early desktop computers. Ironically, the Z80 was an enhanced version of Intel's own 8080, designed by former Intel engineer Federico Fagen. To counter this, Intel developed the 8086. So what are the key features of 8086? Well, it has enhanced support for higher level programming languages, thanks to more robust stack instructions. In software development, frequently used codes segments are structured into subroutines, also called functions or procedures. For example, suppose a program needs to compute the average of 1,000 numbers of pairs. Instead of writing the same calculation repeatedly, we create a subroutine that takes two numbers, calculate their average, and returns the result. The stack stores and manages data and return addresses for this function calls, making program execution more efficient. The 8086 also marked Intel's full commitment to CISC, or complex instruction set computing, while earlier Intel processors like the 8080 and 8085 had already CISC principles. The 8086 fully embraced it, offering an extensive instruction set. So even today, x86 CPUs remain the only mainstream processor that use CISC architecture, as most other CPUs follow RISC, which is reduced instruction set computing. The difference lie in the instruction set complexity. RISC processors use simple primitive instructions, while CISC processors handle more complex multi-step. Okay, okay, let's continue. So, what are the difference between RISC and CISC? So, like I said, RISC processors use simple primitive instructions, while CISC processors handle more complex multi-step instructions within a single operation. Beyond CISC, Intel also tackled memory access performance penalties in the 8086. The processor could also work with the 8087, a separate floating point coprocessor, coprocessor to enhance mathematical computation capabilities. The success of 8086 was tied to another game-changing event in computing history, which is the rise of IBM PC, the most popular. In the late 1970s, the personal computers industry was dominated by Commodore, Atari, Apple, and Tandy Corporation, sealing the market rapidly. IBM entered the scene and released the IBM PC, which became the industry standard. This also set the stage for Microsoft's software dominance, as IBM PCs relied on Microsoft operating system. So the IBM PC's success cemented x86 as the dominant architecture for personal computer, which a position it still holds today. You can see here the videos. You can look at that. Okay. So next is part 4, which is the 32-bit processor, pipeline, and cache. So let's go there. So let's continue. Sorry. So let's continue with part 4, which is the rise of 32-bit pipelining and caching. The rapid expansion of software from simple text-based tools to highly complex and feature-rich products dominated the computing world during the 1980s and 90s. With this expansion came a heightened demand for processors that could handle growing memory requirements and offer more computing power, all while maintaining affordability for consumers. So rise of 32-bit architectures. So in the mid-1980s, the rise of 32-bit processors was crucial in meeting this increasing software demands. While 32-bit architectures had existed since the late 1940s, in mainframe systems, it wasn't until the 1980s that the full 32-bit processors became prevalent in desktop computing. One of the early examples was the Motorola 68020, which featured both internal and external 32-bit data buses, as well as 32-bit address bus. This cheap arithmetic logic unit allowed it to perform 32-bit of operations in a single clock cycle, marking an important leap in computing power. However, in Intel's 8386 released in 1985, would solidify 30-bit architecture as the future for personal computers. The 8386 introduced a set of 32-bit registers, 32-bit internal architecture, and more powerful memory management features. Addressing the limitation of its predecessor, the 8286, which is an improvement, allowed for addressing approximately 4.2 gigabytes of memory, which is a large increase that would support the growing complexity of software. In addition to the 8386 supported a protected mode with paging, which combined segmentation and paging memory management. This allowed the system to use a flat memory model, simplifying memory management and laying the groundwork for more powerful computing. Powerful computing systems, which is the combination of virtual addressing uh, and paging in the 8386 would remain a core feature of x86 processor for decades. So let's move on to the pipelining. Pipelining, as a processor speeds increase, the need for efficient instructions and processing became crucial. Pipelining was introduced to address this challenge, allowing processor to run at a higher clock speed and execute instructions more efficiently. Pipelining divides instructions execution into discrete stages, each handling part of the instruction in parallel as each instruction passes through the pipeline. Its stages operate independently, leading to reduced delays. However, issues such as data hazard and control hazard could disrupt the smooth flow of the pipeline. So data hazards occur when there is a dependency between instructions that causes delay. Control hazard, on the other hand, happen when conditional branch instructions cause incorrect paths to be loaded into the pipeline. To resolve these, techniques like pipelining, bubbling, and operand forwarding are used. So pipeline bubbling insert idle cycles to manage data hazard, while operand forwarding allows data to be passed through the pipeline before it's stored in the main logic. Some processors also utilize out-of-order execution to minimize pipeline stalls. Control hazards are managed by predicting the likely path a branch will take, preventing the pipeline from resetting unnecessarily. And lastly, caching. To further improve performance, caching plays a critical role in reducing the gap between fast processor and slower memory. Cache store a small amount of high-speed memory close to the processor, buffering access to the larger, slower main memory. When a program accesses memory, the cache controller determines which memory block to access. If the block is found in the cache, this is known as cache hit, when offers a significant performance advantage due to faster data retrieval. If the block is not in the cache, it results in a cache miss, leading to slower access times as data must be fetched from main memory. There are different strategies to handle cache updates. Write-through cache, data returned to the cache is immediately also returned to the main memory. This ensures the consistency, but can also slow down performance due to frequent memory access. Okay. Next is write back or copy back cache. These changes are made to the cache are only written to memory when the cache back is replaced. It improves speeds but requiring more sophisticated tracking of modified data. So these caching techniques are crucial for improving system performance, particularly when combined with pipelining, allowing for faster and more efficient instruction execution. And next is how do graphic cards work? So this is the next section. So we're on section 3. A GPU or graphics processing unit is a highly specialized processor designed to handle the parallel processing required for rendering graphics and videos. Unlike the processing unit or CPU, which is designed for sequential task execution, the GPU is built to process large blocks of data simultaneously. This parallel architecture makes GPUs particularly well suited for tasks involving high volumes of data, such as graphic rendering, video decoding, and scientific simulations. Originally, GPUs were used primarily for rendering images and animations in video games and multimedia applications. They handled tasks like transforming and shading vertices, applying texture, and calculating lighting effects to produce 2D and 3D images in real time. However, over time, GPUs have evolved from being strictly graphic-oriented hardware to a powerful general-purpose processor. Today's GPUs are used for more than graphics. With their parallel architecture and high throughput, GPUs have found application in variety of computational fields. Machine learning, particularly deep learning, is one of the areas where GPUs have had most significant impact. The ability of GPUs to handle massive datasets and perform complex matrix operations in parallel makes them the go-to choice for training and deploying AI models, especially deep neural networks. So, for example, GPUs speed up the training process of AI models by executing multiple computations at once. drastically reducing the time required compared to CPUs. In addition to AI and deep learning, GPUs are used in scientific computing, cryptocurrency mining, and video editing. Their ability to accelerate tasks that involve large-scale data processing, such as simulation, financial modeling, and video rendering, has made them indispensable in modern high-performance computing systems. Additionally, with the rise of cloud computing, GPUs are now available in the cloud, allowing researchers, developers, and businesses to leverage powerful computational resources remotely. Modern GPUs contain 1,000 of smaller cores, also called CUDA cores in NVIDIA GPUs or stream processors in AMD GPUs, designed to execute thousands of threads simultaneously. This architecture allows them to perform complex calculation in parallel, making them vastly more efficient than CPUs for tasks that can be parallelized. The flexibilities of GPUs combined with their immense computational power continues to drive innovation in fields ranging from gaming and virtual reality to AI, scientific research, and even digital twins, which simulate real-world systems and environment for analysis and predictions. As the, man- as the demand for high-performance computing continues to grow, GPUs are expected to play an even more central role in accelerating technologies and shaping the future of computing. And next, which is sub operations, which I'll just discuss in here. So I'll try to provide a SAP one simulator. I'll just provide an image. This one, while I talk. So for example, this one. So the simple as possible or SAP1 is a basic microprocessor model used for educational purposes to demonstrate the fundamental operations of a CPU. It's a small and simple computer system that can perform basic tasks like addition, subtraction, data storages, and transferring information between register and memory. SAP1 is built around a 4-bit data bus and uses a single-bit instruction register, making it ideal for understanding how processors execute operation at low level. So what are the key operations in SAP1? So we have already given this in how CPU works, but this here they are. So fetch, the first operation in the instruction cycle is fetching. The instructions from memory, the program counter, PC, holds the address to the next instruction, which is sent to the memory address register, MAR, or MAR. The instruction is that the address is then retrieved and placed into the instruction register, IR. Second is decode. After fetching the instructions, the CPU decodes it to determine which operation needs to be performed. The instructions register is read, and based on the binary code, the CPU determines whether it's an arithmetic operation, a data transfer, or a control instruction. And then lastly, execute. Uh, no, sorry. The third is execute. In this phase, the actual operation is carried out. This could be an arithmetic operations like addition or subtraction, or a data transfer like moving data between registers and memories. SAP1 uses its accumulator, or A, and other register to execute these operations. Which, for example, is if the instruction is an addition operation, the value in the accumulator is added to the value of a memory, or from the memory, and then the result is stored back in the accumulator. Fourth is store. If the operation modifies data that needs to be saved back to memory, the CPU stores the result in memory. This is typically done after the arithmetic operation, like when the sum of two numbers is calculated and needs to be saved. Lastly is the increment program counter. So once the operation is complete, the program counter is incremented, pointing to the next instruction. This allows the CPU to proceed with executing subsequent instructions in the program. So the instruction cycle, the entire process of fetching, decoding, executing, and storing is repeated for every instruction in the program. The SAP1 uses a basic clock cycle to time this operation. ensuring that they occur in consistent and orderly manner. So example operations in SAP1 are addition. The SAP1 can add values stored in accumulator memory and updating the accumulator with the result. Load. This operation loads a value from memory into the accumulator, setting the stage for further calculation. The result 3 is store. The result of computation in accumulator can be stored back in the memory. And jump. A control instructions allows the program to jump to a different part of memory, altering the sequence of operations. So now, let's move on to SAP1 programming. So hello everyone. Today we are going to uh, I am going to present you how a SAP1 circuit works. So the SAP1, or as simple as possible one, is a fundamental 4-bit computer model designed to introduce basic computer architecture concept. So in this one, we'll explain the main components first of the SAP1 and simulate how it executes the given program. So first is the program counter. The program counter is responsible for uh, this one above here. It is responsible for holding the memory address of the next instructions to be executed. So it increments automatically after each clock cycle, ensuring sequential execution of instructions that stores in memory. If required, it can be reset to start the program from the beginning. So next is the MAR, or the memory address register. It's here. So uh, it temporarily stores the address provided by the program counter. It serves as a bridge between the program counter and the ROM, where the program instructions are stored. By isolating the address from the program counter, the MAR ensures a smooth fetching of instructions. Next is the ROM. The ROM is presented here, and this is the main chip, this one, the huge one. Uh, it is where the program is stored in a hexadecimal format. For the given program, the instructions include operations like loading a value, or the LDA, adding a add button, add instruction or add state, subtracting state, and outputting the data, and halting the data. So each instruction has a specific opcode stored in the ROM. And next is the instruction register, or the IR. So here it is in the bottom. Oops. So it fetches the instructions from the ROM via memory register. It splits the instruction into opcode and operand. So the opcode defines the operation to be performed, while the operand specifies the data or memory address. Next is the controller sequencer, just below the instruction register. It manages and controls the signal for the entire system. It ensures that all components work synchronously according to the fetched instructions. For example, it enables loading of data into register, or the activation of the arithmetic logic unit, or ALU. Then next is the accumulator, which is here at the top, accumulator A. So this one uh, is for arithmetic and logic operations. It temporarily stores the value uh, of the result of operations performed by the ALU. For instance, when adding or subtracting numbers, the result is stored here before being moved to the output register. Then the B register, just below the accumulator, is used for the second operand of arithmetic operations. So when there's already a value that gonna be added or subtracted, uh, the value from the B register is sent to the ALU to be added or subtracted from the value of accumulator. Then the ALU, which is stated before, is the addition and subtraction. So it is the input from accumulator and B register, then it solves them and send the result back to the accumulator. Then next is the output register, which will output the display of the total result here, and gonna be shown in the 7th segment. And Next is the clock, which synchronizes all the operations within the circuit. So let's start. Let's start from the operation here. So you can see it's turned off currently. So let's turn it on, which will connect to a ground. Then, as you can see, the program counter is 000, which will be fetched by MAR. So if you click it, it's already there. Then, uh, the instruction register decodes the instruction and the value at memory address 0, which is gonna be 5. So let's start. So as you can see, it's already in 8 because at the ROM is already in 08 at 00. Let's see. You see that? We turn on low and the accumulator is 000. And then let's send, you can see the program counter incremented by 1. And then MAR will take that. You can see. As MAR, as program counter as MAR take the value of program counter, which is 000 earlier, um, MAR then is now gonna be in instruction register, as you can see. So if you look at the instruction register, uh, the first four values will be for the controller sequencer, while the first four digit is based on MAR. So as you can see, we are still in the load or LDA, which is 000. If you are on 1, which is 0010, is going to be add. And if we're going to be subtract, this is 001, 1110. And lastly is 1111, which is the halt. Okay, so let's start. You can see as the ROM is taken, the accumulator takes that ROM, it says there, and then the accumulator is presented with 5. So let's go to our next one, which is 11 here. So let's go. So the counter is still in 0, which is loading. So we have to 5 plus 11 minus 6. So that's 10. So we already added 5 plus 11, uh, which is 19 here. As you can see, just 19. We're still not in 11. So let's load. Let's see. The program counter incremented again, which MAR will take. There you go. See? So now we are at 0001, which is add. So let's send 11 to the B register. So the value 11 now is in B register. So the process is like basically this. The MAR takes the program counter and the program counter increments. MAR then takes the value of uh, ROM, and then ROM sends a uh, instruction register, and then the controller sequencer is based here. So as you can see, 0001 is the same as here, and then the first one here is the MAR. So you can see 1001. Then let's solve it. So 5 plus 11, it will store the sum here in accumulator A. So let's go. So you can see it added into 16. So you can see the ROM is 10001, 10011. So let's go for subtraction. So we need to increment this into, okay, 6. As you can see, it's 0000, 0110. So we have the program counter here. So the instruction register now decodes the instruction. The value of the memory is loaded into the B register. So as you can see, we have 11 and 16. So that resulted in 6. So let's try it again. Now it's 10. So 16 minus 6 is 10 now. And then we're in the output, which we are going to display it here. The value of 10 will be sent in output register. Then it's gonna have an output. So let's go again. EEE. Sorry. 11 to A. Okay, some by 6. Then we're going to display at the next click EEE, which is here, stored in the value of the ROM. Now it is registered. So we have output in EEE. As you can see, EEE, the value is now registered in output. Then the last one, as you can see, is 111, which is output. And the last is FFF, as you can see, this one, which results in halting the whole operations that even if you click the controller, it doesn't do anything. It's just stop intent always. You can see FFF, which is 111, nothing's happening anymore. So that's how a SAP program works. So it increments 4 by 4 now, as you can see. So SAP1 is an excellent model for understanding uh, how the computer system executes instructions step by step by breaking down its component and simulating a program. Uh, this is an insight for the foundation of computer architecture and how they are built upon in more advanced systems. So that's all. Thank you for watching. Have a great day.